Okay, so we finish up with a discussion of Markov chains. Markov chains are a way of applying probability to systems which are changing, which have some variable which is changing over time. Okay, so what we imagine is that we have some ordered list or chain of random variables. We typically call them x0, x1, x2, and so on. And they're looking at something which is, their values is something which is evolving over discrete time steps. Okay. So, for example, we might have something like x0 could be the population in 2020, x1 could be the population of a country in 2021, x2 could be the population of a country in 2022, and so on. Okay. Another example would be if you're tracking the price of some asset which is traded on an open market, then x0 could be the price at 1 p.m., x1 could be the price at 1:05, x2 could be the price at 10 minutes after 1, right, and so on. Okay, now, are these xi going to be independent? Okay, well, I suppose in some cases you could come up with all sorts of examples, so there would be some cases in which they would be. In the examples that we've given, assuming independence would be wrong. Okay, so if you have a given population in 1 year, then the next year's population should strongly depend upon the current population, for example. So,
stocks one could be independent.
The stock one, again, you would probably be able to fit some sort of a model to it. So one thing that is done, for example, is that you say, okay, the stock is worth 1 rupee. Okay? And then you assign a probability. You say that there's 50% chance that it'll go to 1.1, and there's a 50% chance that it'll go to 0.9, and so on. So you have like a binomial model. So, so where you are, where you're going to go next depends upon where you were, right? Similarly, if you had, say, some sort of a random walk, you're at a position 0, then you go to position 1, then you can go to position 2 at each tick of the clock, and you can go to position, say, -1 and -2. And again, you might be saying something like, there's a 0.3% chance that you would remain where you are at the next time click, and 0.4 that you move to the right, and 0.3 that you move to, so. Okay, so the probability that you're going to be at 2 at a given time depends upon being at 1 in the previous time. Okay. All right. Okay. Okay. So we're going to look at a very simple model in which the value of xn plus 1 depends upon the value of the random variable xn, but it doesn't depend upon any of the previous ones. Okay? So if I wanted to model say the weather, the temperature rounded to the high temperature on a given day rounded to the nearest integer, let's say. You could build a model which only depends upon the previous day's temperature, for example. Okay. So let's suppose that, yeah.
In that dependence, though, xn plus 1 depends on xn. That means xn depends on xn minus 1. So even though directly xn plus 1.
Yes, exactly. Indirectly, they could be dependent, but your prediction about what happens next can be made simply based on your current. Right. Okay. So we're going to suppose that each of these xn can take some values from a set s equals s1, s2, s3, and so on. Okay. Now, here's a trick. We can take these, so we call these states. So we say that xn can be in the state s1, s2, and s3. And then we do a little bit of a trick just for, it can be a convenience, is we can also, so let's say that xn had some probability of being in the state s1, right? Well, we could define a new variable, yn, and we could say that yn takes the value 1 if xn is in state s1. And it takes the value 2 if xn is in the state s2, and so on. So we may as well just suppose that if you have a discrete set of states, we could just call those states 1, 2, 3, and so on. Okay? All right. So, and sometimes it might be convenient to start at 0. So 0, 1, 2, 3. Okay. All right. All right. So if xn equals I, right, we say that the system is in state I at the nth time. So a bit of terminology. Okay, so as an example, the students, so we have a bunch of classes. Let's say we have 28 classes in a semester. So x1, x2, x3 is the number class, and then s would be 0, and then the number of students who actually come to the class, s would be 0, 1, 2, 3, up to whatever the enrollment in the class is.
Would that be for like each class?
Yeah, and then the x3 could be the attendance on the third class, right? Okay. So that gives us that's an example of a Markov chain. So if 12 students come to the 7th class, so then x7 is set equal to 12, and we say that the system is in state 12 at time 7. Okay, so Markov chains we're dealing with right now are called discrete time Markov chains. And so we say that there's a bunch of random variables, x, which we call x sub n equals 0, 1, 2, and so on. And they take values in a set S, and S would be some subset of 0, 1, 2, and so on. Okay. Oh, sorry, that got cut off at the end. All right. So we say that this process, we call it a Markov chain, if the probability that the system is in the state J at time n plus 1, given that it was in the state I n at time n, and we list all the previous history, right? So if I know all the states up to the current state xn, right? And I say the probability that the system will next be in the state j, given all of the previous history, that can be calculated just with the probability, calculating the probability that it will be in the state j, given that it was previously in the state I sub n. Okay? So if it has this property, we will call this a Markov chain. Okay, and if the number of states is finite, well, we call it, if the number of states for a Markov chain is finite, then we'll call it a finite Markov chain. So something like this, if you're doing a random walk, that's not finite. It's a Markov chain. A random walk can be thought of as a Markov chain, but it's not a finite Markov chain. Okay, so let's say that we have a Markov chain, and then we're going to say that the probability that the system will next be in the state j, given that it's currently in the state I will call that p sub ij. Okay? And we call these the transition probabilities. Okay? So for example, let's say I made this finite by chopping off infinitely many pieces. Okay, let's come up with a new diagram. Okay, so it can be in the state 1, and then there's a 30% chance that next it will be in the state 2. There's a 30% chance that it will next be still in the state 1. And that leaves 0.6. That leaves 0.4 probability that it will next be in the state 3. Okay. Let's say from 2 you can only go back to 1. Say it's 0.5, and being next again in the state, remaining in the state 2 is 0.5. Okay. And let's say that if you end up in the state 3, you can only go to the state 2 with probability 1. So then, let's see. What's P of 2, 3 in this example? What's P of 2, 3? Right, P of 2, 3 means what's the probability that if you are in the state 2, that next the system will be in the state 3? 0. There you go. Okay. What about P of 3, 1? P sub 3, 1 means what's the probability that if you are in the state 3 currently, the system would next be in the state 1? 3, 1. Okay, is 0. What's P of 3, 2? You know, okay, so these are the PIJs, right? My Markov chain, sorry, my Xn is in a given the system is in a given state. The states are labeled 0, 1, 2, 3, and so on, or 1, 2, 3, and so on. Pij means what's the probability that if the state were currently in the state I, that it would next be in the state j. Okay. Okay, and these are assumed to be fixed, so it doesn't depend upon, these don't depend upon the time. Right? So if you started off at 1 and you wandered around and eventually you came back to 1, then the same probabilities for transitioning to the other states, they would remain the same. Okay. Okay, so, right. Okay, so this just says that same thing over again. Okay. Okay, so state transition matrix and the state transition diagram. Okay, so the matrix, you have these Pijs, and we make the matrix P, which is unfortunate because we're also using that for probability. Maybe I should have written that a different way, but okay. We're all getting tired at this point in the semester. Okay, so the matrix P is just this matrix with the Pijs in it. Okay. Why do I want to use a matrix? Well, if I use matrices and vectors, then all the machinery that was developed in your previous linear algebra course, all of that is now available to be used with discrete time Markov chains. So it's useful if I can describe things using matrices and vectors.
This will always be square matrices, right?
And this will always be a square matrix, yes. Okay. Okay, and once again, the Pij means if the system is currently in the state I, what's the probability that it will next transition to the state j? Okay, so the Pijs are probabilities. They will always be greater than or equal to 0. And if you sum these Piks, if you sum over k, then they should sum to 1. The probability should sum to 1. Okay. Okay. Okay, so that matrix, if you had a finite number of states, right? If you had a finite number of states, then you can get this matrix P, and that basically tells you everything you need to know. Right? That information is all stored in that. Okay? And you can also have a state transition diagram. And that's basically this thing that we've drawn over here. Call that a state transition diagram. Okay, so this state transition diagram and this P, matrix P, they both have the same information in them. All right, so what does this say? It says that if you are currently in the state 1, then in the next time step, there's a 0.8 probability of being in the state 2. And there's a 0.2 probability of remaining in the state 1 in the next time. Okay? If you're in the state 2, there's a 0.5 probability of remaining in the state 2 in the next time. and there's a probability, a 0.5 probability of transitioning to the state 1 in the next time. Okay? Well, this says the same thing. The probability of 1 to 1 is 0.2. Of 1 to 2 is 0.8. Of 2 to 1 is 0.5. And of 2 back to 2 is 0.5. Right? So this diagram and this P both have the same information. Is that okay? Yes?
I thought of this as having headings. Then we put 1, 2 and 1, 2.
Sorry.
If we thought of this matrix as having headings, then we would put the headings as 1, 2 on the columns and on the rows.
Right. So your right. Your Pij's in the matrix, the entries are Pij. So I is the row and j is the column.
Yeah.
Right. Okay. And this means the probability of going from a state I to the state j. Okay. All right. So, what are we going to do with these matrices?
Sir, can we do one more matrix, like a bigger one?
A bigger one? Okay.
But not 2 by 2.
Well, it has to be square. Okay? So, all right. The matrix P for this one, 1 to 1 is 0.3. 1 to 2 is 0.3. 1 to 3 is 0.4. Okay? 2 to 1 is 0.5. 2 to 2 is 0.5. 2 to 3 is 0. 3 to 1 is 0. 3 to 2 is 1. 3 to 3 is 0. This entry? This one? Okay. Well, okay, so the way I've drawn this, if you're at the state 2, I'm saying you can either be at the next time step, you can be still at the state 2 with probability 0.5, or you can go from the state 2 to the state 1 with probability 0.5. And there's 0, you cannot go from the state 2 to the state 3. So 0.
So the row sum must be equal to 1.
Yes, yes, yes. All right. Okay. All right, so both of these have exactly the same information with them. This might help you visualize things, right? Especially if the diagram sort of naturally breaks up into 2 clumps or something. It might be helpful to visualize it. This one you can actually do calculations with. Okay, so we'll see what calculations can be done with this. Okay, so state probability distributions. Okay, so once again, you have a Markov chain, a bunch of variables, and each one of these is saying what this says, this takes the value of the state at the time n, and the states will assume take values 1, 2, 3 up to r. Right? If there were infinitely many, then we couldn't really use a matrix. Because then we need an infinity by infinity matrix to do it. Okay. Yeah. Okay, so this, if my P for this system is going to be an R by R matrix. So if there were infinitely many states, like in a random walk, I couldn't really use a matrix. My matrix would have to be infinity by infinity, right? Yeah, so that wouldn't work. Okay. So what we're going to do is I've defined a matrix. Now I'm going to define a row vector. Okay? I'm going to suppose that my initial I'm going to be, instead of having P multiplying a column vector, I'm going to have a row vector multiplying P. Okay? All right. Now, let's say that I have I have these x0, x1, x2, x3. x0 has to be in some state. And I'm thinking of that as the system that I'm thinking about. x0 takes the value of its initial state. And it could be in the state 1, 2, 3, 4, so on. Let's suppose that I know, or I can reasonably estimate, the probabilities concerning the initial state. Right? So I could say, well, no, it's not going to come from here.
How is it not the diagonal?
Well, okay, so let's say that so let's say that you have a service that starts at 8 a.m. in the morning, right? So there's a queue. There's some sort of a gate, and there's a queue at the gate, right? And you know, the number of people who are lined up at 8 a.m. in the morning at that gate every day, that changes. So I have some historical data, right? So I have an idea that the probability that the number of people at the gate is 1. So my S, 1 might represent having 1,000 people at the gate, right? And 2 might represent having, well, let's say 0 to 1,000. And 2 might represent 1,000, having 1,001 people at the gate to 1,100 people at the gate, or something like that, right? So I have, from historical data, I have an idea that the probability that we'll be in the state 1, the number of people at the gate when we open, that's why I'm saying 0 initially, is some probability by historical data, whatever that is, right? Then I have the probability that I could be in the state 2, right? Then I have some probability that I could be in the state 3 initially, all the way up to I will be in the state R initially, right? Yeah.
In the matrix above, their final probability. The one that
This is not related. Yeah, this is related to transitions. This P is related to transitions. This is saying, what's the probability? This is about being in a state rather than transitioning between states. Okay? So, again, in my example, having this many people, so 0 to 100, let's say And then this one is 100 to 101 to 200 and so on, right? And let's say there's a maximum capacity. We can't have more than 500 people in the queue. If there is, then we cut the queue off and we tell people to go home or something. Okay? Or we have a server and it can only handle 500 requests at a time and puts them in a queue, and if it's full, then you just don't get a connection to that server on the internet or something like that. Okay? So you've got a queue, and the queue could be in state 1, state 2, state 3, up to state R. Okay? So I'm saying just define a row vector with these probabilities, call it pi of 0. It's convention. I'm sure there was a reason for it originally. I'm not sure what the reason is. All the texts use pi for this. Okay? So, there's a row vector. Okay? Now, let's talk about the transition, the probability distribution of n. Okay? That's a probability that this is the row of probabilities, and the first entry is the probability that the system at time n is in the state 1, that the system at time n is in the state 2, that the system at time n is in the state 3, and so on. Now, that will depend upon, well, xn, the probability that xn has some value depends upon, there's a dependence upon the value at xn at time n minus 1. Right? Okay. So anyways, for now, these are just definitions of row vectors, okay? So here I can define pi of n. That's this probability distribution for xn. Okay? We'll suppose that this one is known, let's say from historical data, and we're interested in being able to calculate the other ones. Okay? All right. Okay. So, if you know pi of 0, can you calculate pi of 1, pi of 2, pi of 3, and so on? Okay? So let's suppose that we know pi of 0, and let's see how we would work out pi of 1. Right?
Are R and N supposed to be equal, or like can they be different values?
They can be different values. Right? So n is the time, R is the total number of states. So you could have just 2 states, but it could be oscillating back and forth for many times, right? Okay, so we use total probability. The probability that x1 is j is given by saying, what's the probability that x1 is j given that x0 is equal to k times the probability that x0 is equal to k. Now these are known. And you sum over all the possible values of k. So that's the probability. Okay, so yeah. Let's say you had something like this. Okay. So let's say that if you're at system 1, if your system is in state 1, then there's a probability 1.0 that you go to a state 2. Okay. Let's say that if you're at a state 2, there's a probability 0.5 that you go to state 1 next. And there's a probability of 0.5 that you go to a state 2 next. Okay? And if you're at if you're in the state 3, then the probability of being in the state 2 next is 1. Okay? There's a diagram, shows us how our Markov chain is working. Now, let's say that your system, let's say it resets every day. Let's say that it always starts in the state 1 at time equals 0. What's the probability that at time equals 1, it could be in the state 3? If you're guaranteed to start at, if you're guaranteed that you will start at 0, okay, so if at time equals 0, you always start at 1. Okay? So, if you always start at 1, what's the probability that at time equals 1, you are in the state 3?
Sir,
Sure.
every transition changes time. So if I go from 1 to 2 or 1 to 3, it's going to change time, right?
Well, no. So the time changes, and at each time change, it's possible that you've transitioned your state.
Then there is 0 probability.
Then there's 0 probability. Yes. Okay. Now, let's say that we start off randomly. What if 30% of the time we initialize with a state 1, and 70% of the time we initialize with the state 2? Okay? Then what is the probability? So x0 equals 1 with probability 30%. And x0 equals 2 with the probability 70%. Okay? Now, what could x1 be? Well, okay. So, let's see. If x0 starts off at 1, okay, so x1 could be 1, 2, let's say it could be 1, 2, or 3. Right? What are these probabilities? Well, I could have started off at 1 with probability 30%, and then I would have had to go to 2. So, okay, I could have started off at 2 with probability 70%, and then I could have gone to 1 with probability 1/2. I could have started off at 3. Well, I couldn't have started off at 3. Okay. Okay. So, what's the probability that I initialize with a state 1 with probability 30%, and I initialize at state 2 with the probability 70%, what is the probability of being in the state 1? 0.35. How did you work that out?
Because the probability that you start at position 2 is 0.7. And
Yeah.
from 2, if you're going to go to 1, that's 0.5.
Yeah.
So you multiply them.
Okay. What's the probability that you're in the state 2 if you initialize at state 1 with the probability 30%, and you initialize with 2 at the state 2 with 70% probability, and you initialize with the state 3 with 0% probability, then what's the probability that you are in state 2? Right. You could have gone from 3 to 2, but it wasn't in state 3, right? And so the only way to get to 2 at time 1 is from here, and there's a 30% chance that you were here, so there's a 30%. Okay? So
Not the ability to like stay where we are. Would we add the individual probability?
yes. Yeah, and we have to add the individual probabilities depending upon where we were previously, right? So that's total probability. Yes.
The question you just asked, was it that what is the probability that x1 equals to? Or x0 equals to?
No, I'm saying x0 represents the initial state.
Yeah.
And I'm saying you can initialize, your initial state could be 1 with 30% probability,
Yeah.
and it could be 2 with 70% probability, and it could be 3 with 0% probability.
Okay.
So once you have that, and you know the transition probabilities, then what's the probability that at time 1, you would be in state 1 or in state 2 or in state 3? That's what I'm asking. Well, okay, so this is, right? So this is your initial, right? When you were multiplying probability, this is your initial state, right? You have a probability in being initially at state k with this probability. And then you have this conditioning. This is just total probability. And what are these things in here? These are the PIJs that I was talking about, right? And what are these things? This is that pi of 0. These are the entries from pi of 0 that I was talking about. And what's this sum? This is that row vector pi of 0 times that matrix P.
So weren't we supposed to multiply the row vector times the p? Over here it's
Yeah, no. It's, I mean, you can move this over to the other side. Yeah. Okay?
So
Yeah,
in the over here,
yeah.
the second bit is, or if we think of x0 as being in state 1, then it would be 0.3 at the other end, and then given that we're in state 1, j will then be state 2, so that's going to be 1. So it's going to be 1 into 0.3, hence we're getting to state 2. If we just put in
Yes, if you plug in there, the probability of x1 being 2 is 1 times 0.3. This is in your matrix P, and this is your from your pi of 0, the probability distribution for the initial state.
But we're still plugging in individual values and not multiplying matrix.
Well, okay, but I'm saying that this is where that if you want to see where that matrix is coming from, then you can look over here. Okay. So, like I said, this conditional probability, these are the transition probabilities pkj, right? And these are coming from your pi of 0. So, here you go. If I know the probabilities about the initial state, if I know the probability that the state will be initially in, the the probability that the system will be initially in state 1 or initially in state 2, initially in state 3, that's this row vector pi of 0. Assuming that that's known or it can be estimated.
This row vector in our example is 0.3, 0.7, and 0.
Yes. Right? In our example here, that pi of 0 is 30%, 70%, and 0%. Okay? And this p are the pij's. These are these numbers over here. Okay.
Isn't there an issue here though?
Hmm?
Like we find pi of 1 from here and then we use pi of 1 to find pi of 2.
Right. So if we have pi of 1, we can find pi of 2.
Every time that we do the multiplication, since
Yeah.
there's only one row of
Right.
our row vector,
Yeah.
we will, okay.
Yeah. So pi of 2, well, take pi of 1 and then multiply by the matrix on the right. And you'll get your pi of 2. Or think of it as, I know this, well, multiply it by p squared, and I'll get pi of 2. Okay, and in general, pi of n is pi of n minus 1 times p, or that's the same as pi of 0 multiplied by p on the right n times. Okay. Okay. So let's say you have a system, right? And you have some, there's your pi, and it can oscillate between values 0 and 1, right? It can stay in its current state with probability 1/2, or it can transition to the other state with probability 1/2 in the next time step. Okay? What would be, supposing we know for certain that this system will initialize in the state 0, right? Then what's pi of 0 in this case? Right. So in this case, I know that pi of 0, I know that it's going to initialize in the state 0 with probability, and it will definitely not initialize in the state 1. Okay, so that's for pi of 0. So what's x3? What's the probability? Okay, so then pi of 3 is equal to 1, 0 times this matrix cubed, right? And so once I've calculated pi of 3, then this asks, what's the probability that x3 is equal to 1? Well, I'll look in the second entry of pi of 3, and there will be the probability that I'm looking for.
We have to like do the matrix multiplication every time.
Yeah.
Do like 2 power 17 or something.
Yeah, okay, so, all right. So when you're doing matrix power, you remember how to take powers of square matrices, right?
You have to multiply them, right?
Okay, well, all right. If you have to raise a square matrix to a very large power, what do you try to do?
Like make it a triangle.
You try and diagonalize it, yes.
So we have to like go echelon.
Yeah, so you have to do the diagonalization procedure that you learned in your linear algebra class. Okay. Well, I'm not going to ask you to take 17th powers on the final exam or something.
Just like making it into a triangular matrix.
Yeah, if your matrix is nice, you can diagonalize it. You can't always diagonalize it, so it can become triangular. But for something this small, I assume that you can take the third power. Yeah.
Just break it up into 3 matrices and then multiply it into
No, you have to do the, like I said, for this one, the easiest thing to do is just to multiply the matrix 3 times. Yeah, yeah. Okay. So, so for example, then, you can, when you're, say, looking at populations, you can, again, you would think of it in terms of a histogram, that the initial population could be between this number and this number, that's state 0, with this probability, and so on. And then you apply your matrix for how your population changes. And then you get, you get a spread of values pi of n, right? So, anyways. Okay. So, right, the pi ij's, again, they were transitioning in one step, right? So, transitioning in transitions in 2 steps. So you're going, what's the probability that you're in I, and then after 2 steps, you will be in J? Well, here you can think about, well, how do I get from I to J? I have to transition from I to something, and then from that something to J, state J, right? Well, then you're just multiplying these one-step transition probabilities. And again, in terms of matrices, just p squared. So p squared, if you multiply p squared, right, the entries in p squared, right, the ij entry in p squared is the probability that if you were in step I currently, you would transition to step J in 2 steps. Okay? Okay. Well, okay, so you have a matrix P, right? And that's got these Pij's in it. And just so that we can distinguish, let me call them Pij of 1. So those entries Pij, they say what? They say that if the system was currently in state I, the probability that at the next time it would be in state J is this number Pij, right? Well, P squared, that has a bunch of entries. Let's call them Pij of 2. Well, that says these entries, the ij entry of this matrix, that's the probability that if you were currently in the state I, then in 2 time steps, you would be in the state J, right? And in general, p to the power, multiplying p by itself k times, is the right? That has entries we can call Pij of k. That means this is the probability that if you were currently in the state I, then in k time steps, you would end up at the state J. Okay. All right. Okay, so this idea in generality is the it's called the Chapman-Kolmogorov equation. Okay, Kolmogorov was the great Soviet mathematician. Came out of the Moscow School of Mathematics. And so this is in terms of these m-step and n-step probabilities. And again, this is the probability, this contain the entries here. If you take p and you raise it to the power n, the entries that you have, the ij entry of this is the probability that if you were currently in the state I, then in n steps you would end up in the state j. Okay, so that's the very elementary introduction to Markov chains. Yes?
Can you go over the m plus n thing? Because I'm confused.
Okay. Okay, so you don't have to worry about the m plus n business. You just have to understand this, okay?